idea? Are the people attending there in one room, or everyone is from their own virtual location?
Here we are here are the students. We are in a room,
Oh, very
but
nice.
there's another students that are online.
Okay, very nice.
And we share.
I see. And I am projected on some projector there in the room.
Exactly.
Okay, very nice.
So give me a second, and we start. Give me 1 moment, 2 minutes, please.
I see. Yeah, sure. Take your time. And do you have a way for people to ask questions if they're in the room? They can just speak, or maybe you will repeat the question if there is something.
Okay. Yes.
Oh. Oh.
Okay, so we are ready, and Jacobo is going to introduce you. So please go ahead, Jacobo. Yes.
Hello, Professor. How are you?
Hello. Good. How are you?
I'm fine. Okay, so shall we start?
Yeah, sure. I'm ready to go.
Okay. So our speaker today is Enricopajer. From Italy, our speaker did his undergraduate studies at Scuola Normale Superiore in Pisa. After that, he completed his PhD at the University of Munich. Afterwards, he was a postdoctoral researcher in the United States at Cornell University and afterwards at Princeton University. Following his time at Princeton, he became a junior professor at Utrecht University in the Netherlands, where he continued his research before joining Cambridge, specifically the Department of Applied Mathematics and Theoretical Physics, where he is currently a professor. So he's a faculty member, continuing his work at the forefront of cosmology. His talk today is on open system approaches to cosmology. So thank you for being here with us, Professor. We're very happy.
Yeah, perfect. Yeah, ready to go. So thank you very much for the kind introduction. And please do let me know if you cannot hear me or if you cannot see my slide, because I only have limited understanding if you can see my slides, but hopefully you will be able to see them. You should see the title slide, an open system approach to cosmology. So let me know if it is not visible. Okay, great. And also, since I don't know the audience very much, I don't know who's sitting there and what your background is, please feel free to interrupt me as much as you would like, especially at the beginning. It will help me a lot making this talk, pitching this talk at the right level so everyone can understand a little bit. So if I give something for granted, please stop me and ask me what I mean. I'd be happy to do it. Okay, so here the main idea of this talk is a different way to think about open problems in cosmology, which is inspired by the study of open system, both in classical and quantum mechanics. And the goal of this talk will be to develop a theory of cosmology, including, of course, dynamical gravity, which is an intrinsic part of cosmology, from an open system point of view. And I will argue that this is probably essential to make progress in the field. So let me first acknowledge the spectacular contributions of my collaborators. Here is Santiago, who's recently left, just last week left Cambridge and joined Chicago. so he's closer to you guys for his first postdoc, Tomakola, who's a postdoc at DAMT, and Leonard Daphner, who's my current PhD student. This is based on 3 papers. 2 of them are up there, and I forgot to write the third one that just came out maybe 2 months ago. And I will give you an overview of these 3 papers. But if you want more details, these references should be useful. So the way I would like to structure the talk is start with a short motivation. Why should cosmology be approached with an open system point of view? And then I'll give you a gentle introduction to open system. I was educated as a high energy theorist, as a particle physicist, as a quantum field theorist, but I never learned any quantum field theory or any quantum mechanics for open systems. So I had to learn it in the past 2 or 3 years. So I think it's useful to review this in a pedagogical way. And then I'll show you how you can use this approach to describe important phases within cosmology, or if you want, from a field theory point of view, typical theories that we encounter, such as the theory of a scalar field as relevant for inflation. So I will describe an open theory of inflation. A spin 1 field, as we encounter in electromagnetism, and I'll show you how to formulate a Lagrangian, or if you want, a functional description of electromagnetism in a medium. When I say an open system, that it will be clear is the same as thinking of the system in the presence of a medium. And finally, with these 2 warm up, I will be finally able to tackle the main goal of this line of research, which is to develop a theory of gravity, of Einstein gravity, but in the presence of an unknown medium. And that will be my theory of open dark matter or open dark energy. And I will conclude with an outlook. As I said, please interrupt me at any time. I'll be happy to take questions. Okay, so here it's a very general slide. Cosmology, we're trying to describe the evolution of the universe, and there are many open questions. Some of them are related to the first fraction of a second before the hot Big Bang. We believe there was a phase of inflation, but we don't know what the degrees of freedom were during this phase, what their interactions were, what their symmetries. We don't even know if this phase can be described within quantum field theory in curved space-time or requires abandoning the notion of locality that is common to quantum field theories and maybe some other fundamental principles. We don't really know. Of course, we try to describe it within quantum field theory. Another phase, which is how to connect inflation to the hot Big Bang. This is the phase of reheating. We don't know the coupling to the standard model, what the intermediate evolution. And more recently, of course, we know that more than 95% of the universe is made of dark matter and dark energy. Dark matter is perhaps the less mysterious. Maybe it's just some weakly interacting particle of some sort. But if it is a particle, its mass is uncertain by as much as 80 orders of magnitude, probably the most uncertain quantity in physics and presumably in science overall. We don't know how it interacts with the rest of the dark sector or if it ever interacts with baryons. Dark energy, even more mysterious. It's related to fundamental problems such as the cosmological constant problem. It may require or may not modifications of gravities, additional degrees of freedom, no minimal coupling. So of course, why am I reviewing these very basic and well-known problems of cosmology? Because I would like to draw your attention to the fact that they all have something in common. And they have at least 3 things in common. Number 1 is that they all involve something that fills space and time. I'm going to call this something a medium, for lack of a better word. Okay, so during inflation, there is something everywhere. That's what makes the universe accelerate. During dark energy, there is something that fills space and time, makes the universe accelerate again. Dark matter, again, is everywhere all the time. And so they are space-time filling medium. This is very different from the setup that we have in particle physics, which is how we learn quantum field theory. In particle physics, the whole point of a particle collider is to make the collision point as empty as possible. So you can really study the pristine details of the interaction of just 2 particles or 3 particles. Perhaps if you have a hadron colliding like protons, it's more complicated, but still the collision takes place in vacuum. In cosmology, this completely is the opposite. The whole universe is filled with stuff. is never in a vacuum. And in fact, the whole point of cosmology is precisely to describe the stuff. You cannot take away the stuff and still do cosmology. If you take an empty universe, that's not cosmology. Okay, so in some sense, cosmology is closer to condensed matter. You're really trying to describe the property of some medium. The second thing that those three problems, dark matter, dark energy, and inflation, have in common is that we do not know their microscopic description. Okay, this is in contrast with other theories, I don't know, like this table or quantum chromodynamics. In principle, we know what is the microscopic description, but is in fact intractable. It just QCD becomes strongly coupled, and unless we use lattice techniques, it's very hard to describe. The quantum mechanics of this table is very complicated, but at least in principle, we know it. For inflation, dark matter, and dark energy, we don't know the microscopic theory. Not even if we wanted to solve it, we just wouldn't know where to start. We can only propose theory. And finally, the third thing that they have in common is that we cannot probe inflation, dark matter, or dark energy directly per se, but we can only probe their gravitational interactions. As far as we can tell, these three things, they only interact gravitationally. We have never observed any non-gravitational behavior of these entities. So all the measurements we do, from the curvature, primordial curvature perturbations from the early universe to the distribution of matter and the acceleration of the universe, they're all gravitational. Okay, so these are the three things that they all have in common. So what is that we need from a theory point of view? What is the field theory that we need to describe such a system? It needs to be a theory that allows for an unknown medium, stuff around the field, space, and time. It needs to be a theory of gravitational degrees of freedom because all the observable are gravitational. So the metric will be a dynamical variable, so it has to be a theory of gravity. And also, we only want to describe the macroscopic behavior of gravity. Probably it is too ambitious and presumably impossible to write down the microscopic theory. If I ask you write down the microscopic theory of this piece of material, it would probably be impossible for you for any object in this room. On the other hand, if I give you a piece of glass, of metal, the first thing you would do is to describe its macroscopic property. Is it transparent? How much does it weigh? Does it conduct electricity? Does it conduct heat, etc.? So perhaps this approach is also useful for dark matter, dark energy, and inflation. So the goal here is to learn from a quantum field theory point of view how to write down a quantum field theory for gravity with a medium as an effective theory. This is the open problem that I will solve through this talk, and I will give you the theory by the end. Okay, I'm going to start with a gentle introduction to open system, but I wanted to pause just to see if there are any questions or clarifications or remarks at this early stage.
No question, Professor.
Perfect. Okay, so what are these open systems? Well, I didn't know what it is, but this is what it is. There's a big system, you divide it in two, and you call one thing the environment, and the environment is there, but you don't want to measure it directly. And another part, you call it the system. They two interact with each other, but you can only measure properties of the system. So this is what we call an open system. Okay, so from this definition, you see it's very general. Pretty much everything is an open system. Me, you. Okay, so how do we describe open system from a field theory point of view? Instead of starting with the full-fledged construction within quantum mechanics, let me start with a much simpler heuristic model, just to give you an idea of what the new physical phenomena are. Let's say that there is some degree of freedom that I call phi. Phi could be a scalar or something more complicated. And let me assume that the medium we're studying is homogeneous and isotropic and doesn't change in time. I would like to know what is the type of dynamics that this degree of freedom can experience. I'm going to assume a separation of scale such that at low energies, so long time scale and long distances, all the degrees of freedom of the medium that is present are inactive, they are gapped, and there is only one effective degree of freedom, perhaps which remains light because of some symmetry. Then this degree of freedom may obey some differential equation, and a prototypical differential equation is this equation, which usually is called the Langevin equation. It has the usual Klein-Gordon form, box phi plus v prime. Okay, so this is what you would have for any scalar field with a potential. However, you can write two new things. One, I don't know if you can see my cursor. One is in red, is gamma phi dot. This is a form of dissipation. If you kick this scalar field, it will slow down because of this term. The second one is a form of noise that I'm going to call psi. This equation is a bit different from the type of equations we usually solve because it's a stochastic differential equation. The left-hand side, the right-hand side, the noise, is given to us only through its expectation value, only through its averages. So you cannot know what this noise does deterministically, but you can only know what it does on average. The prototypical example of this system would be a little grain of pollen or dust in air. It gets kicked by the molecules of air. You cannot see the molecules of air, but you can describe this, the motion of this, through Brownian motion. And on average, it gets kicked to the left as often as it gets kicked to the right. So from a low energy effective theory, we can assume that the statistics of this noise is particularly simple. It can only be correlated at the same time and at the same space. This is because we assume that the medium has a much shorter time scale and much shorter length scale, and therefore all of its correlation look like contact correlation from our low energy point of view. So the 2-point function of this noise could be a delta function or a derivative of a delta function, and the expansion in derivative here corresponds to an effective field theory expansion. So you already see that there are two phenomena that we are not usually describing in a field theory, such as those we use for particle physics. One is noise and the other is dissipation. These will be two of the characteristic phenomena that we will attempt to describe. Okay, so as often, although we want to solve some equation, it is useful to rewrite those equations in terms of a function, or in terms of a variation of a function. Okay, so that's why we use the action principle, and we write Lagrangians and Hamiltonian instead of working at the level of the equations of motion. There are many reasons why we like to do that. We can see conserved currents and conserved charges through Noether theorem. We can easily generalize to quantum mechanics because you put it into a path integral. E to the I, the action, will give you the quantum theory. Well, if I only give you the equation of motion, it's harder to move on to the quantum version, and many other reasons. However, as you may know, you cannot derive these equations of motion from the variation of an action that is invariant under time translations. Okay, if you try. However, there is a trick. There is still a function that you can write down. It's not an action, but it's called an open functional. And instead of explaining why this trick works, I'm just going to tell you what the trick is. The trick is that you take your degree of freedom phi and you double it. From one phi, you get two, phi plus and phi minus. The plus and minus is just to distinguish them from each other. Now you write down a function of phi plus and phi minus that I'm going to call an open effective functional. It could be an arbitrary function of phi plus minus an arbitrary function of phi minus. This is the same that you would have if you had the simple Lagrangian for a closed system. However, you can also allow a functional in which the two of them talk to each other, interactions of phi plus and phi minus. This function f that depends on both phi plus and phi minus is known as the Feynman-Vernon influence function. It's what encodes the effect of the medium. Now, usually, if I give you this function, or what do you do with it? Well, you get the equations of motion. How do you do that? You perform a simple rotation. You go from phi plus and phi minus to their even combination, phi plus plus phi minus over 2, that we call phi retarded, and in their odd combination, phi plus minus phi minus, that I will call phi advanced. Okay. And now you take the variation of this open effective functional with respect to phi a at phi a equals 0, and that is the equation of motion. If you do it this way, this theory allows you to describe the new phenomena of dissipation and noise that you wouldn't otherwise be able to describe in the standard formalism. There is a beautiful way to understand why you need to double the field, which is what this drawing at the top right refers to, but I don't have time to discuss that unless people really want to ask about it. Okay, let's see from this toy model how we can derive that Langevin equation from the variation of this action. In this action, let's write the typical action of a scalar field, d phi plus squared plus v of phi plus. This would be the usual action that you have for a scalar field with a potential. Minus the same thing with phi minus, d mu phi minus squared minus v of phi minus. The minus sign will be clear in a moment. And the key point is that now I can write phi plus phi minus dot. If I hadn't doubled the degree of freedom if I only had phi, I could not write phi dot, meaning I could write it, but that would just be a total derivative, and it wouldn't contribute to the equation of motion. That's why you cannot get gamma phi dot. However, because I doubled the degrees of freedom, the variation of this, when I go to the Keldysh basis of retarded and advanced fields, and I vary with respect to phi a, indeed I get the equation with a gamma phi dot, which is exactly what I want. So this doubling of the degrees of freedom is only a formal trick. In fact, the number of degrees of freedom is the same as before, but phi a can be thought as an auxiliary field that allows me to capture these more general phenomena, such as dissipation and noise, as I will explain in a second. Okay, so that was the warm-up. That was the intuitive introduction to the topic. Now I'm going to give you a little bit the more formal and the more fundamental derivation of open system, and I will switch to the quantum mechanical language, unless there are some questions. So let me pause here.
No
Okay.
questions, Professor. Thank you.
Very good. Thank you. So in this case, let me just review how we do quantum mechanics. In quantum mechanics, the two fundamental objects are Hilbert space of states and operators, an algebra of operators acting on this Hilbert space. When we have a generic state in quantum mechanics is a linear operator on the Hilbert space that satisfies the following three properties. It's called rho. We usually call it a density matrix. It must be Hermitian, rho dagger equals rho. It must be positive definite, so its expectation value on any state is bigger than 0, and the trace is normalizable, so it can be normalized such that trace of rho is 1. Any such rho defines the state of the system. If trace of rho squared is 1, then the state is pure and can equally be thought as a vector in the Hilbert space. And this is how we usually learn quantum mechanics. If trace rho squared is not 1, then the state is mixed. And it's also an totally acceptable state. It just cannot be identified with a single vector in the Hilbert space. Good. When a system is described by a density matrix, how do we compute observable? Well, the expectation value of an operator, for example, phi to the n, is computed by taking the trace of rho times the operator, in this case, trace of rho times phi to the n. Let's write down this as a path integral. Rho will be the time evolution of some rho initial using some unitary time evolution operator from t initial to t. And if you remember, the time evolution of rho requires, because rho is something like cat bra, it requires a time evolution operator to the left and a time evolution operator to the right. And so there are two time evolution operators. One is a U and the second one is a U dagger. One involves the cat and the other involves the bra. If we insert the identity, a resolution of the identity based on eigenstates of the field operator that I called phi, we can rewrite this as the initial density matrix times the transition amplitude from phi prime to phi mediated by u, the operators phi n, and then the other transition amplitude. Of course, the transition amplitude from phi initial to phi mediated by the time evolution operator is exactly what the path integral is e to the is. So we can see here there are two copies of the path integral, one corresponding to u from phi prime initial to phi, that's going to be e to the is for some action of the theory, and a backward time evolution corresponding to u dagger from phi initial to phi, but going backward because of the dagger, e to the minus is. Okay, so this can be written as a path integral, so this expectation value can also be computed using the functional language rather than the operator formalism as the path integral over some forward time evolution e to the s, backward time insertion of the operator phi to the n, and then backward time evolution, possibly average over some initial state. This explains why I had to double the fields, because now at a given time t, there are two fields, one field that lives on the forward branch and one that lives on the backward branch. And to keep track of what I mean by phi of t, I have to call it either phi plus of t or phi minus of t. Finally, it also explains why the phi minus, the part of the action with phi minus has a minus sign in front because it corresponds to backward time evolution. This is the famous Schwinger-Keldysh formalism, sometimes also called closed time path or in formalism. And the initial condition can be any density matrix, although for this whole talk, the initial condition will always be the Bunch-Davies, which is at short scales the same as the Minkowski vacuum in quantum field theory. Just a little intermezzo. Let me mention that as long as we are sticking to a closed system that starts in a pure state, this formalism that I just described works perfectly well. So the in formalism can be used to describe a closed system in a pure state. There is nothing wrong with it. And when you do so, it will always give you exactly the same result as the in-out formalism. The in-out formalism is the formalism we use to compute correlation functions, which then we amputate with the LSZ reduction to compute amplitude, scattering amplitude. In fact, these two formalisms, in and in-out, are equivalent to each other, and they are equivalent to the Euclidean formulation of the theory. They just correspond to different Wick rotations. In the complex T-plane, the in corresponds to the green line forward and then the orange line backward. The in-out corresponds to the rotation of the second in to the out, and the Euclidean corresponds to the rotation to the of 90-degree clockwise of the in-out formalism. All of this formalism for a closed system in a pure state, all the same. Although it wasn't appreciated that this is the case, not just in Minkowski, but also in the sitter. A lot of the cosmological literature was always using the in formalism, assuming that this is something completely different, but for a closed system, it's just the same. In fact, we recently showed this both formally and explicitly, that you can do all calculations in cosmology, especially in early universe cosmology and in the theory of inflation and the generation of cosmological perturbation, using the in formalism as people have been doing for 25 years, or the in-out formalism. They always give the same result. The advantage of the in-out formalism, and there is only one propagator, which is the time-ordered two-point function, so-called the Feynman propagator. Well, the in formalism has at least 4 propagators: time-ordered forward, time-ordered backward, non-time ordered, and non-time ordered in the opposite ordering. So the in is a little bit more complicated, but both of them can be reduced to a set of Feynman rules. Okay, let me finish this intermezzo and move on with the story of open system. If we are describing a system that is not closed but is open, there is a crucial difference in the description. And then in and in out are not the same. In is the only description possible of the system if the system is an open system. Let's see what the difference is. Imagine we start with a closed system in which we know everything. And let's say that of all the degrees of freedom phi, we only keep track of some of them that we call pi, and we don't observe others, let's say sigma. Since we don't observe sigma, if we want to compute expectation values of pi, we should integrate out sigma. So imagine you have some path integral. Here I didn't write the sources, but suppose that the only sources you care about are the sources of pi, and you want to integrate out sigma. The original path integral, in which you describe the full system, will be e to the I s pi plus sigma plus minus I s pi minus sigma minus, because this is a closed system. Okay, there is no mixing of plus and minus. When you perform the sigma plus integral, there is a 2-point function of sigma between the plus branch and the minus branch, which couples pi plus and pi minus. The effective theory that you get from this is not of the form e to the I s of pi plus minus s of pi minus. Pi plus and pi minus now talk to each other. The effective dynamics of pi is now that of an open system, which is fundamentally distinct and more general than that of a closed system. Now we're describing new physics, new phenomena that cannot be described in the in-out formalism. Few technical comments only for the experts in the audience. Maybe I can go briefly. Even though it looks like I double the degrees of freedom, the boundary conditions of the advanced field is going from 0 to 0, so it's actually not a dynamical degrees of freedom. So the number of dynamical degrees of freedom is the same as before. Assuming a separation of scale, we can attempt to write down the effective action as a local function of pi a, pi r. This will not be true in general, but if there is a separation of scale, it will be true. And so we can expand this effective action in power of the fields and derivatives according to some power counting scheme. I also mentioned the presence of noise, and for that we have to work a little harder, so let me mention something about it. Imagine that in the action you write a term which is quadratic in the advanced field, e to the I beta pi a squared. Naively, it looks like this doesn't contribute to the equations of motion because the variation with respect to pi a at pi a equals 0 does not contain this term. However, to see the emergence of the noise, we have to perform the Hubbard-Stratonovich transformation. E to the minus beta pi a squared, which is what this term would correspond to in the path integral, can always be written as an integral in the psi of e to the minus psi squared plus I psi pi. This is the trick. This is just a mathematical identity. It's the property of Gaussian integrals. If you now compute the equation of motion by taking the variation with respect to pi a, you will see that there is a source term in the equations of motion, psi. And psi, from the path integral, you see, is just a Gaussian field with a variance dictated by beta, which was the coefficient of the pi a squared term in the first line. This is how noise is described by this formalism. This is a very simple example. This formalism can describe an arbitrary form of noise that is not Gaussian, but all kinds of non-Gaussianities, and it doesn't necessarily have to be a delta function, but it could contain also derivatives. So here we recover the Langevin equation, but from a functional description. There are several rules for what open effective theory can arise from a consistent UV closed effective theories. We don't want to write down open effective theories that could never arise from integrating out the degrees of freedom. And so one important constraint comes from demanding that the UV completion at high energy in the full theory is unitary. If that UV completion is unitary, which is essential for probabilities to make sense, then this implies certain constraints. The three constraints are somewhat obvious if you think of the density matrix. You need the density matrix to be Hermitian, positive definite, and normalizable. What the in path integral does for a living basically is to generate the density matrix for you. And so you need to preserve these properties. In terms of the pi r and pi a variables, these constraints simply mean that the effective action must start linearly in pi a. In other words, if pi a is 0, the whole action has to vanish. You cannot have a term which only depends on pi r. That's not allowed by unitarity. It has to have the interesting property that if you send pi a into minus pi a, and you do a complex conjugate of the action and put a minus sign, the action remains invariant. This strange transformation has an interesting effect. It tells you that if you have a term in the action that is even in pi a rather than odd, then unitarity demands that its coefficient is purely imaginary. Usually we think of unitarity as demanding that something is real. Well, here it actually demands that it is imaginary. And finally, the imaginary part of the action has to be positive so that the path integral converges. Okay, so this was the end of my gentle introduction to open system. Now I'm going to give you three examples of a scalar, a vector, and a tensor theory, unless there are some questions.
Hi, yes, I have a question. Regarding to this last point that you told us of
Yes.
effective field theories in this open system approach, I wonder if this noise and this medium that is considered could be explained as or with a non-open approach. I mean, if this medium, this noise could be part of an underlying theory, you know, if this noise and the medium can be explained in a fundamental way somehow.
Yes, yes. I think the idea is that it can. It's just that we don't know that theory. So similarly, if you're trying to describe the motion of a grain of pollen in the air, and you are Mr. Brown, you don't know that air is made of molecules. However, you notice that you can describe it in terms of Brownian motion. It is true that later on, you may realize that Brownian motion actually is explained by kinetic theory, assuming that air is made by a bunch of molecules. But if you don't know, you have to write down a low energy effective description. Imagine that you are Bardeen, Schrieffer, and you try to write down superconductivity. You may not be clever enough to know how to describe superconductivity microscopically because it's a very complicated theory, but you can try to describe it effectively. So the idea is that all of this noise and dissipation, they do admit a microscopic closed system description, but that description is either too complicated or we are not clever enough to find it. And so I'm proposing to use this effective description to explore those possibilities that we have not been clever enough to discover yet.
Okay, and this unknown physics or these degrees of freedom that are hidden in the effective field description could be associated with infrared, energies instead of ultraviolet. It is possible to have an effective theory in which you integrate out degrees of freedom of low energy.
It could be, but typically when you do that, yes, for sure. Typically when you do that, however, you generate correlations at long distances and long time scales because light physics can correlate at long distances and long scales. And so the system would still be described by an effective open system, but the effective functional would not be local, would be a non-local functional. In fact, largely speaking, the whole of the physics of electromagnetism in a medium is described in terms of a non-local in time system. And so you can definitely go there. And however, when the system is non-local, it's harder to define an effective field theory in the way we do in particle physics, and you have to work rather in terms of models. You say, I know the non-locality will be of this type or of that type. And that's, if you want, how the whole book of Jackson deals with electromagnetism in a medium. They integrate out light degrees of freedom, and they say, well, this is a model. For example, the Drude model is one such model of non-locality in time.
Okay, thank you very much. That's very interesting.
You're
I have
welcome.
another question. I'm sorry, but
Yeah, sure.
regarding to this model in which you introduce a dissipation term, this gamma one, a model
Yeah.
of inflation, a very simple one. That term usually in inflation models comes from gravity. So my question is,
that's correct.
if this noise could be associated to those degrees of freedom.
This will be in addition to the 3H phi dot term that we always discover when we couple minimally to gravity. This is in addition to.
I see, but you cannot substitute the gravitational term by a noise one.
Not in this theory, no. I mean, because the gravitational term is constrained because you want inflation, scale invariance, quasi-exponential expansion, and that fixes H. And then on top of that H, there is additional dissipation from additional degrees of freedom. That's the main idea.
Okay, thank you very much.
You're welcome. Any other question?
Professor, here on the auditorium, it's okay.
Good, okay. So let's see how to use these ideas in the simplest possible setting, which is during inflation, where we're only trying to describe effectively a single scalar degree of freedom. I'm going to take the decoupling limit. So gravity for me will be non-dynamical for the next 5 minutes. And so we only describe the scalar degree of freedom. Many of these ideas are not new to us or to our work. Some of these ideas of inflation taking place in the presence of a medium go back to the 90s, and the ideas of warm inflation, much work by many people that I mentioned here, Boyanovsky, Holman, Burgess. There is a nice work by Lopez Nacier Porto, Senator, and Saldariaga, and Hong et al. That also studied this system. So we're definitely not the first one, but let me show you how we would proceed from our point of view. Well, we use the general effective field theory rules. Rule number 1, tell me what the degrees of freedom are that you care about. Number 2, write down all possible interactions compatible with the symmetries you have chosen and the set of principles. As Anna, I think, was asking, is that perhaps locality is not a relevant principle. Perhaps the interactions are really non-local because you integrated out some infrared physics. However, in that case, it's hard to write down all operators because there are infinitely many of them. Here, instead, I will assume that the theory is local, and then there will only be a finite number of operators. If you don't want locality, you need to work with a model, a particular form of non-locality. And number 3 is that you choose a certain power counting so that you can truncate all of these operators to some order, and you work with that. Okay, so in this case, as I said, during inflation, we only care about one scalar degree of freedom. This is the Goldstone boson of time translations. There's a beautiful story that goes under the name of the effective field theory of inflation that I don't have time to review, but the short story is that the only scalar degree of freedom we care about, which is the one that in a certain gauge can be thought of as the trace of the metric degrees of freedom, of the spatial part of the metric, can also be described as this Goldstone boson. We work in the decoupling limit, so the only theory we want is only this Goldstone boson. There is just one scalar. Well, then we have done a lot of the work, how to write down the theory of a scalar. We take the symmetric combination of pi plus and pi minus. We double pi, it's a single scalar, we double it to pi plus, pi minus. We compute the retarded and advanced part of it, which is the symmetric and antisymmetric. And now we try to write down the most generic theory for this degree of freedom. We wanted the UV theory to be unitary, so we had those 3 constraints as before. I insist on locality because I want to work within this effective field theory setup. And presumably there are constraints from causality and subluminality. For the moment, I'm not completely clear on what those constraints are. So I will simply assume that the speed of propagation of this object is less than the speed of light. Finally, I need to impose some symmetries. The scalar that describes the primordial perturbations in our universe has to obey some additional symmetries to be identified with a component of the metric, which are ultimately related to the diffeomorphism invariance of gravity. To cut a very long story short, we need to understand how these symmetries that we usually learn in the closed system approach, how they work in an open system. So global symmetries in an open system, they're always broken to the diagonal combination because of the boundary conditions. Gauge symmetries are only partially broken. The off-diagonal combination is broken by cross interaction between the plus and the minus branch, because if you perform a gauge transformation on the plus branch, which is completely different from a gauge transformation in the minus branch, terms that couple these two branches will not be gauge invariant. And so that diagonal combination is broken. However, the combination in which the gauge transformation is the same on the plus branch and on the minus branch, that will be unbroken. As a consequence of this, the relevant symmetries here are the one in which pi a transform like a normal scalar under time translations and spatial boosts, while the retarded component transforms as a Goldstone boson, non-linearly. So it shifts under a time shift, and it shifts under a Lorentz boost. So this is interesting that they have this distinction is essential to get the physics of the system right. And I wish I could spend more time here discussing the physics of Goldstone bosons of time translation and boost, but I will just state this. So now we write down the most generic theory compatible with these symmetries for these 2 degrees of freedom, pi r and pi a. Okay, there is the thing that you could write always, pi r dot, pi a dot. So first of all, remember, it has to be linear in pi a, or quadratic, but it cannot be 0th order. And if we want to write down the free theory, it has to be pi r times pi a or pi a squared. These are the only options. And then we put derivatives. Since pi r is shift symmetric, pi r always have to appear with derivatives, so pi r dot. And then this line here contains all possible terms to lowest order in derivative. The first 2 are the same terms you would put for any scalar field moving at the speed cs. Cs is the so-called speed of sound. It can be different than from the speed of light because boosts are always broken in cosmology by any cosmological background. The third term in red, pi r dot pi a, this is the dissipation. And you can see that this is on top of the dissipation generated by the minimal coupling to gravity, which comes from the a of t. A is the scale factor. And finally, in the blue terms of order pi a squared, those are all noises. The first term is a delta function noise. The second is a time derivative of the delta function noise. And the last one is a spatial derivative of the delta function noise. Given this theory, we can predict everything we want. We have to compute the relevant propagators. There are, in some sense, 3 propagators, pi r, pi r, pi r, pi a, and pi a, pi a. The clever choice of the Keldysh rotation is that the pi a propagator or 2-point function is 0. And the only non-zero propagators are the pi r. This is the so-called Keldysh propagator. This is the one that will give us the power spectrum. The power spectrum is the main observable from the early universe, the one that we measure in the data, in galaxy surveys, and the microwave background. And the second propagator is the pi a, pi r, which in the operator language is nothing but the retarded and advanced propagator. Okay, so given these 2 propagators, we can compute everything we want about the free theory, and we can write down Feynman diagrams to compute the interacting theory. It's illuminating to look at what this propagator looks like in flat space. The retarded advanced propagator that describe the propagation of the correlation of signals You see it's 1 over omega squared minus CSK squared, the same as a normal field moving at speed cs, but it has an I gamma omega. So the poles of this propagator are moved into the complex plane. And in fact, the frequencies omega now have an imaginary part. And if you notice, the imaginary part is always negative, so that e to the minus I omega is always a decaying signal as you move toward the future, so that dissipation has the right sign if gamma is positive. So these are the dispersion relations. They are dispersive in the sense that there is an imaginary part of the frequency as well as a real part that represents oscillations. The Kalish propagator is more complicated, but can be computed from this. The expression is given below. The Kalish propagator is always proportional to this amount of noise. Notice that in a theory with dissipation, the memory of initial conditions is lost after a certain amount of time of order 1 over gamma. And so the power spectrum is always generated by the noise rather than by the initial condition. This is the example of the 2-point function in Minkowski. You see that it's always proportional to beta. Beta is the amplitude of noise. And depending on which noise you put in, it has a completely different K dependence. So the characteristic of noise really changes the properties of the theory. In the zeta, it's just the same, except that we have to deal with more complicated functions. Now the mode functions are Hankel functions. And for those of you expert in working in anti-de Sitter or de Sitter, you will recognize the argument of this Hankel function, and you will see that it is the usual formula, except that the dimension of space has been shifted from 3 to 3 plus gamma over h. This is related to what Anna noticed before, that this gamma actually looks like it's the same as a shift in the Hubble friction. The Hubble friction is h times d, where d is the number of spatial dimension, usually 3. And now if you put a gamma, it is as if you lived in a number of dimensions different from 3. The propagators can now be written down straightforwardly. The power spectrum is always 1 over k cubed because that's dictated by scaling invariance, which we preserve in our theory. But the amplitude changes and is given by this nice formula here at the top, which was already known before our work, but we rederive it from this point of view. And now we can take different limits of this formula. If we assume that the medium is in thermal equilibrium, which in general we don't, then the dissipations and the fluctuations are related to each other by the fluctuation dissipation theorem, and we recover the well-known power spectrum of warm inflation. More generally, these two are unrelated, and we can get any amplitude of the power spectrum we want. To study interactions is straightforward. You do the same exercise to cubic order. Write down all terms that have 3 pi's. One has to be always an advanced pi, pi a. And so it can be pi r squared pi a, pi r pi a squared, or pi a cubed. And they're all written here, and we have studied all of them. These are interactions now, so they generate non-Gaussianities, which are most easily seen in the 3-point function, and you can compute, based on this interaction, those 3-point functions. As was noticed before, many of these interactions are dictated by nonlinearly realized symmetries, and so they are unavoidable. Some of these interactions, for example, in the second line, you see the interaction proportional to gamma. And the interaction tells you that if the free theory is dissipative, then the theory is necessarily interacting. And the size of the interaction is proportional to the dissipation coefficient gamma. This gives a strong connection between the 2-point function and the 3-point function. Okay, so these are the nonlinearly realized symmetries that I mentioned before, and they allow us, oh, I'm sorry, what this? I thought I had skipped the slide. Oh yeah, sorry, I forgot to go to full screen again. Finally, all of these correlators have a very distinctive shape, and to build intuition, you can perform the exact calculation in Minkowski, where the result is a rational function with singularity, and the singularities of the denominator correspond to when the triangle formed by the 3 momenta of this 3-point function has a 0 area. those are so-called folded singularities, and they are unique because they never happen in a closed system. They are unique to an open system. Or in other words, they require you to have a universe that is not empty, but that has some stuff. The presence of that stuff is exactly what creates this enhancement when the triangles have zero area. The beauty of this approach is that usually these would be singularities, actually divergence when the area of the triangle is zero, but the divergence is always shifted by the dissipative term, this I gamma, move the poles such that the denominator is never zero. And so there is a large enhancement for folded triangles, but it's never infinite. And so we always remain within the validity of the effective theory. This is extremely interesting phenomenologically. I don't know how many of you follow primordial non-Gaussianity and cosmological inflationary phenomenology, but these are distinctive shapes that have been and are being searched in the data, both of the cosmic microwave background and of galaxy surveys. In other words, if you look at the data and find folded non-Gaussianity, then you know the early universe took place in the presence of some medium. So it was in some sense an open system. Okay, I'm going to pause for some questions and then move on to the vector theory.
Here in the auditorium, no questions, Professor.
Good, thank you. So I realize that I'm going a bit more slowly than I expected, but I don't want to rush too much. So maybe if you can give me 10 more minutes to conclude, I hope that's not a problem. So now I'm trying to develop a theory of open gravity. This requires to figure out how we use gauge invariance, because we know that gravity, we're trying to describe only 2 degrees of freedom, but the metric naively has 10. And understanding diffeomorphism or gauge invariance in general is complicated in this in formalism, in this Schwinger-Keldysh formalism. So we decided to teach ourselves how to do it in the simpler case of electromagnetism, which is a free theory. So I'm going to give you the answer of how you do it. You take the electromagnetic field, capital A, you double it, it becomes A plus A minus. You take the symmetric combination that I simply call A, because that's going to be the physical one, and the anti-symmetric combination, that's the advanced combination, which I call little a. That will be an auxiliary field. Now the crucial point, to ensure that there are no ghosts, a sufficient condition, perhaps not necessary, this is not clear to me, but definitely sufficient, is that we impose gauge transformation on A mu, so that we only describe 2 degrees of freedom and not 4. You know, one of the degrees of freedom of the photon usually is a ghost, and it's only because of gauge symmetry that you can remove that and get a consistent theory. So we're going to impose gauge transformation on capital A, but not on little a, because little a is non-dynamical. There is no need to impose any gauge transformation on it. And we write down the most generic free theory to all ordering derivatives. This is actually the beauty of this approach. This is valid to all ordering derivatives if it is local. And it is made by these 4 terms. This here, the F is the field strength of capital A, while A can appear without derivatives because there is no gauge symmetry on little a. Something remarkable happens in this theory. It has 4 parameters. Those parameters, gamma 2, gamma 3, gamma 4, actually are function of omega and k, so they can be expanded in derivative at low energy. But because this theory is free, it can be written as A nu m mu nu A nu, because it's a free theory. And gauge symmetry tells me that this matrix m mu nu has a 0 eigenvector, so its determinant has to be 0. But if the determinant is 0, it must also have also m dagger needs to have a 0 eigenvector. And so there is also a gauge symmetry on little a, even if I didn't impose it ever. This is necessarily an emergent, perhaps accidental symmetry that we call advanced gauge invariance. What's interesting about this symmetry is that is actually not a normal shift of A mu going to A mu plus D mu of something, but the amount by which A mu shifts is proportional to gamma 2, which in a second I will show you is a dissipation parameter. So there exists a gauge transformation of this theory only at the linear level, which is proportional to the dissipation parameter. If we couple this A mu to an external source J mu, we get the Maxwell's equation by varying the action with respect to little a. And the Maxwell equation has some terms that are familiar. D mu F mu nu equals J nu, that's the usual form, but there are new terms proportional to gamma 4 and capital gamma, which is simply gamma 2 plus I omega. This additional term will change the way photons propagate in this theory. The dispersion relation is written here, and as you can see, gamma 4 can be thought of as birefringence. Gamma 3 represents the speed of light in the medium that can be different from 1. And gamma 2 represents the dissipation of light as it propagates. And the transverse degrees of freedom will propagate as e to the minus gamma t, which is exactly what we wanted to describe the dissipative propagation of light in a medium. Another last interesting aspect of this theory that I wanted to mention before I conclude is that the current that couples to little a is not conserved. It couldn't possibly be, because if you just take d mu of this equation, you find that the current is not conserved. Rather, it is conserved in a non-standard way. So it does obey some equation, but it's not the usual equation d mu j mu equals 0. This makes perfect sense because j mu only represents part of all the current of the system, the one that we're keeping track of. Other charges that are moving around corresponding to the medium, they have been substituted for their expectation value, which is a function, a gauge invariant function of the electromagnetic field. This is key for gravity. We will allow for a stress energy tensor that is not conserved in an open theory. And this is perfectly consistent with the equations. I'm going to finish in the last 1 minute, if you allow me, with open dark energy, or I could simply finish here if you guys are in a rush.
Professor, go ahead, please. We are
okay. Thanks.
We are able
Good.
to.
So for the last,
yes.
Okay, thank you. That's very kind. So for the last couple of minutes, I'll tell you how to do gravity, which is somehow conceptually, now that we understand electromagnetism, it's not infinitely more complicated, but it has many new features that emerge. The simplest, the most interesting one is that in electromagnetism, we were able to introduce dissipation by keeping the degrees of freedom to 2. While in gravity, if you introduce dissipation, you select the preferred reference frame that breaks diffeomorphism, automatically introduces new degrees of freedom. In the simplest case, a scalar. In the more complicated case, a scalar and a vector. And so what is the idea? This is a very long story. There is some interesting work by a variety of people, Toshifumi Naomi and collaborators, for example, here. They have a nice related constructions. I'm just going to present the result of our work. You write a theory for G mu nu, open, so you double G mu nu into G mu nu plus G mu nu minus, take the symmetric combination that we simply call G mu nu, because that's going to be the physical one, and the anti-symmetric that I call A mu nu. That's going to be an auxiliary field. Now, I write down the open functional. The term that is proportional to A mu nu is nothing but the Einstein equation. Remember that the equation of motion is the variation of S with respect to the advanced field. And so this tells me that I can write down any 2 tensor that depends on G mu nu as Einstein equation. And I will organize this Einstein equation in terms of a derivative expansion. To keep the number of degrees of freedom to a minimum, I'm going to assume that the system is still invariant under 3 spatial diffeomorphism, but not under time diffeomorphism. So the system that I'm describing will be an open system for 2 degrees of freedom plus a scalar. So the 2 tensors that live in the metric plus a scalar. In the presence of this, I can write down all possible operators in the action that can be organized into a tensor M mu nu and another tensor N mu nu rho sigma. And these tensors are any combinations of objects that are 3D diffinvariant. It could be Ricci, Riemann, but it could also be extrinsic curvature of a preferred hypersurface. There are similar expressions for the noise. The theory has 3 degrees of freedom and has an extremely rich phenomenology, and I believe that probably has a lot to say about dark matter, dark energy, and inflation. I don't even have time to describe much of its phenomenology, so I'll give you the simplest possible theory, which is a particularly tuned case in which the theory actually preserves the full 4 diffeomorphisms, and so only has 2 degrees of freedom. So I never even break Lorentz invariance. Then the most general form of the Einstein equation is any number times r mu nu plus any number times g mu nu plus higher derivatives equals t mu nu. Okay, I can always combine these terms such that I get the Einstein tensor g mu nu and t mu nu on the right-hand side. But now that there are new corrections, for example, the coefficient, I don't know if you ever noticed that there is a tuning in the Einstein tensor. So r mu nu comes with exactly the coefficient -1/2 g mu nu r. That tuning is what ensures that through the contracted Bianchi identities, t mu nu is conserved. But now t mu nu does not have to be conserved, and so you can simply have r mu nu minus any number times g mu nu r, and any number is allowed by this theory. In particular, the t mu nu will not be conserved by itself. This theory has a very rich phenomenology. If we want to try to make it realistic, we should probably add the standard model, and we're going to assume by hand as an additional requirement that the energy momentum tensor of the standard model is conserved. However, the energy momentum tensor of dark matter does not need to be conserved, and in fact, in general, is not. So this is a modified theory of standard model plus dark matter, in which dark matter is not conserved per se, but obeys a modified conservation equation in which the Laplacian of t mu nu is proportional to the derivative of t standard model. Notice the asymmetry. The standard model sources dark matter, but dark matter does not source the standard model. This is characteristic of an open system. There is no need for the sum of the two to be conserved. This is a very non-standard conservation equation, but is completely compatible with, and in fact, it is a consequence of the modified Einstein equations in an open system. It gives a one-parameter deformation of lambda CDM that can be fit to the data, and we are in the process of fitting this to the data. And there are interesting implications for the fitting of baryon acoustic oscillations and the cosmic microwave background, especially of the most recent results from the DAISY experiment. But unfortunately, I don't have time to review that here. So I'm very over time, so I'll just have my last slide. Because we have written down a theory of gravity, there is a lot we can do. In particular, the simplest thing you can do is to describe the linear theory, which is just the propagation of gravitational waves. This is the equation we get. As you can see, it contains the usual terms, box gamma ij plus 3h gamma dot, that represents the propagation of gravitational waves and their redshift due to the Hubble friction. But now the gravitational waves can propagate at any speed different from the speed of light and can have birefringence. This birefringence term is new, and it is very interesting. Usually in electromagnetism, birefringence, which represents the rotation of the polarization of a photon as it propagates, is a conservative effect. Here, the leading order birefringence is a dissipative effect, and conservative birefringence will only arise at one derivative higher. So actually, this is a much leading compared to the standard birefringence. This should be used to fit the propagation of gravitational waves as measured by gravitational wave interferometers such as LIGO, Virgo, Cagra interferometers, and it will put constraints on the macroscopic properties of dark energy as a medium through which gravitational waves propagate. Let me conclude. I think an open system approach to cosmology is pretty much essential at this point, given what we know about the universe. We have written down a theory of gravity with all the right principles, and there is a lot of rich phenomenology to be studied and a lot of interesting theoretical questions to be understood. So thank you very much for listening, and sorry for going over time.
Yes, thank you so much, Professor, for this amazing talk. Here we are on the auditorium, so we have some time for questions on the public online or here from you guys. If you have questions, please approach to the computer.
Hello.
Hello.
Nice talk.
Thank you.
I have a question about, well, I'm going to give some context. In normal QFT, we usually work in a flat space-time and without a medium. Here we have a medium, and I want to ask this. Does the presence of dissipation selects a frame reference or selects a gauge? Because, well, dissipation means that there is a preferential frame where...
Yes, yeah, absolutely. You're right. So that's the correct intuition. Lorentz symmetry is necessarily broken by this medium. There is a preferred frame, which is the frame of the medium. And if you boost with respect to it, you will experience a very different physics. You will be bumping into the medium. So yes, Lorentz boosts are necessarily broken. In a non-gravitational theory, that's the end of the story. In the gravitational theory, this breaking also comes with an additional degree of freedom representing the deformations of the medium.
For example, for massless gravitational waves, I think they have two polarizations, but this presence of the medium will I think, will add another polarization, or like a mass term.
Yeah, I wouldn't call it necessarily a mass term. This additional scalar degrees of freedom is also massless. In the high energy limit, it can be thought of as a Goldstone boson. And so it does enjoy a shift symmetry that prevents a mass term. So here, both the graviton and the scalar will not have a mass term because of the symmetries of the problem.
Okay, thanks.
Yeah, thank you. There are more general cases where a mass term can be written down, but they require more complicated symmetry breaking patterns. And they're more related to the study of massive gravity. But here we try to stay clear of that.
Okay. More questions online or here on public? Online, if you, yes, Marco, come.
Hi. Hello.
Hello.
So, the first question I have is regarding the Xi term in the Langevin equation, because you said that this should come from a correlation function. So I wonder, do this term should be measured within the system you're working on, or how do you get to know it?
The idea is that in the low energy theory, this complicated two-point function or n-point function of Xi is described by just a few numbers. For example, the lowest order, the two-point function is just a delta function times a number. Let's call that number beta. So that number needs to be measured, is an effective coupling constant of the theory. Or like in any effective theory, you need to measure the coupling constant, but after you measure it once, then you can use it to predict all kind of observable with that same value.
Okay.
So you should think of this beta the same as an effective coupling constant. Let's say like the 3-point function interaction of a pion in the chiral Lagrangian, for example. So you have to measure that, or you can try to model it or fit it to the data.
Okay, got it. The other question I have is in the part of working with OpenGR, it was not very clear to me how the Langevin equation plays role.
Oh, excellent question. Yeah, I went way too fast on that. So my Einstein equations are modified in two ways. Usually it's G mu nu equals T mu nu. Now I have G mu nu plus something equals T mu nu. That something is another generic tensor. That's the first modification. The second modification, that inside T mu nu, now there is also a noise that is only known stochastically.
Okay.
So when you solve that equation, for example, the solution, let's go to the Newtonian limit. In the Newtonian limit, you just get the Poisson equation that says Laplacian phi equals rho. Okay, that's how the Newtonian potential is determined by a distribution of mass. Now it will be Laplacian phi equals rho plus noise. So if you want to know the Newtonian potential, there is always some noise. This noise should be detectable in experiments.
Okay.
So it's another prediction of this theory.
Right. Okay. And my last question is about this theory not being compatible with Lovelock's theorem. So I wonder what is the highest order of the derivatives in the equations of motion?
This theory evades the assumption of Lovelock's theorem because it's not derived, because it's not derived from an action. So it actually evades the theorem in the sense that one of the assumptions is invalidated. And that's particularly interesting because it is derived from a functional, but that's a functional of double degree of freedom. And that gives you the possibility to derive many other operators that Lovelock would say you cannot derive. So that's the technical assumption. But I think it's completely consistent because it comes from an open system rather than a closed system.
Because sometimes when Lovelock's theorem is violated, you can get orthogonal instabilities in the equation. So I was just wondering.
Yeah, we were worried about instabilities, but here, because we impose gauge invariance on G mu nu, actually all of our degrees of freedom seems to be healthy and do not violate unitarity. We were very worried about it. That was the main reason why we did all of this study of gauge symmetry, because it is gauge symmetry that saves the day. If you just write down any terms, you typically get ghosts.
All right.
And then you're screwed. But imposing gauge symmetries on the retarded degrees of freedom is what ensures the absence of ghosts as far as we understand. And I think we demonstrated that in the electromagnetism, and I think it is true for the same reason in gravity.
Okay.
But you're right that is the main concern. That's why, in some sense, all of this work was needed, so that we know what is the right unitary theory to write down. So that's a good point. Yeah.
Okay, great. Thank you.
Thank you for the comments.
Do you have a question? Okay.
Hello. Maybe
Hello?
that would be too much basic, but why do we have to write a non-conservative equation of currents when we work on a gravitational theory?
Well, the idea is that the total T mu nu is conserved, meaning if you knew the total theory, if you knew exactly where dark matter and dark energy and whatever the rest of the dark sector is, then the sum of the whole thing would be perfectly conserved. So the full theory is closed and is G mu nu equals T mu nu, and T mu nu is conserved. However, we don't see all of the dark sector. We don't have any other way to see where dark energy goes if it is dynamical. We don't know if there are additional contribution to the dark sector, maybe dark radiation. And so because of this ignorance, because we don't actually measure the dark sector, there is no practical sense in which we can test if the dark sector is conserved. So it's much more useful to say, okay, there is some T mu in the dark sector, we don't know, we don't measure it. We describe it in terms of this open system. And so from that point of view, there is no need to require that the T mu that appears on the right-hand side is conserved itself. Yes, in some sense, if you want, it's kind of necessary. If your desire, suppose that I ask you, write down the Einstein equation from which I can derive the propagation of a gravitational wave that dissipates. We know gravitational waves dissipate as they propagate, right? They bump into stuff, and so they decay a little bit. The size of the dissipation can be large or small depending on the system, but we know they dissipate a little bit. Clearly, if you put a dissipative term on the left-hand side, then the contracted Bianchi identity tell you that the right-hand side is not conserved. So this has to be the case. It's because we are not following the full T mu, but only the T mu in the low energy effect direction. But I think that's the right perspective to have. I think that's the right thing to feed to data, or the right thing to describe.
Okay, thank you.
Maybe it's a bit philosophical, but I hope it's convincing.
More questions, guys? Online questions? One question more here.
Hello, can you hear me?
Yes, loud and clear.
Yeah, in an introduction, I asked myself, how do you say, or how do you figure out the formalism for closed system, and how it is equivalent to the QFT amplitudes? How do you figure out these two?
How do I prove it that they are equivalent?
Mm-hmm.
Oh yes, there is a nice derivation that we have in the paper, which I probably did not present, but I think this one, maybe I'll just show you this slide because it's actually very simple. Oh yes, perfect. Let me just share the screen because I think one figure will make it very clear. Yes, can you see this? Can you see my slide now?
Yeah, I can.
Good. So imagine that we're doing a path integral over the informalism. And so this is the complex time plane. We go forward with a little bit of an imaginary part, and then we come backward with a little bit of a positive imaginary part. This is the I epsilon prescription of the informalism. And I want to prove that is equal to the in-out. What I do is that I put an infinite amount of time evolution from minus infinity to plus infinity. The key point is that this I can always do for free because time evolution from minus infinity to plus infinity is just a phase. And so this is true if you go from in a closed system from the vacuum to the vacuum. Infinite amount of time evolution from minus infinity to plus infinity is always a phase. So up to a phase, you can always add this whole contour. And then you can just close the line here. Forward time evolution and backward time evolution cancel each other. And so these red lines represent the cancellation. And you're left with only forward time evolution from minus infinity to plus infinity. This is the formal derivation. This is in terms of drawing, but exactly this drawing can be turned into equations. And we do this in the paper. And this is the equation. You start with in-out, you introduce the phase, and you prove that the phase cancels, and you get in. This is a non-perturbative argument. It requires you to believe that the infinite amount of time evolution from minus infinity to plus infinity is just a phase times the same state, which I believe is true. So that's the derivation.
Okay. Thank you. Interesting.
You're welcome.
So more
That is in my
questions?
paper with Yaniv Donath. So Payer Donath, there is the whole paper is about proving that, if you're interested in more details.
All right. Thanks.
Well, I think that there's no more questions, so we want to thank again, Professor. Here.
Great. Thank you very much for the invitation.
Yes, we hope that you could attend to another time.
Yeah, with pleasure. And thanks a lot for the many interesting questions. It made it much more interesting for me too.
Thank you so much, Professor. So see you.
Okay, talk to you soon. Bye, everyone.